Hello and welcome. I am David Henderson, the founder and CEO of NewScale Robotics and NewScale Technologies. Thank you for watching this on-demand presentation for the 2021 World Conference on Quality and Improvements. Today I am discussing how the latest smart automation solutions can elevate your quality team, and more specifically, the new opportunities to implement robotic calipers in your inspection process. Today I will provide an overview and examples of how robotic part gauging, that is, part inspection, can make your organization more competitive. These are our learning objectives. Identify the greatest benefit of robotic calipers. Understand the new business case for implementing Agile inspection tools. Follow the best practices for implementing automated part inspection in high-mix, small batch manufacturing. Today, we believe tens of thousands of quality departments are underserved by automation when compared to other aspects of manufacturing. This video tells a story called Cobots Meet Quality. A routine task may be to measure features on small parts with a manual digital caliper and record the results on a notepad. These measurements may be pass-fail or digitized later for statistical tracking and analysis. The small batch of parts is quickly finished, but then his supervisor brings in a much larger batch of the same parts. This inspector seeks a better way, a more innovative and productive solution. He sees the potential of collaborative robots and smart gripper calipers. Here is a tool that he can integrate and deploy without third-party integrators. He stands up, moves his chair out of the way, rolls in a Q-spin workstation that fits in the same space without the need for special guarding. He teaches the system to inspect all the features on his part and digitally record the data in just a few minutes. He launches the inspection program, which continues even when the lights are turned off. This video illustrates the new paradigm of collaborative Agile automation and its far-reaching potential. The new possibilities include serving high-mix, small-batch manufacturing, the 90% that are not automated today. Optimize how people and robots work together. Automate dull, dirty, or dangerous tasks that drag down your staff. Enable a new generation of robot programmers. Robots as easy to program as your smartphone. Robots that you teach instead of program. And an ecosystem of apps for every challenge. Collaborative robots are a key enabler of Agile automation. Today, collaborative robots are the fastest growing industrial robot segment. The word Cobot was first coined in 1996. Cobots are different. They're safe, they're force and speed limited. They increase your team's skills, productivity, and engagement, and they're inherently networked to Industry 4.0 systems. Today, there are more than 100 companies making cobots, including virtually all the established robot brands. However, the market share leader is a new company. Universal Robots started in 2005, and by the end of 2020, had shipped a total of 50,000 robots. One of the most unique features of cobots is they operate in close proximity to people. This picture shows 3 cobots safely working next to an operator on a food packaging line. We believe there are strong incentives to innovate quality processes with robotic inspection. The motivations include eliminating dull, repetitive, and error-prone measurements, increasing capacity, and throughput, reducing operator-to-operator variations, providing real-time digital data for process improvements. Manual part gauging using physical contact remains an essential tool for quality departments. Examples include digital calipers, micrometers, and specialty gauges such as height gauges or ring gauges. Manual inspections have inherent variations due to people. Inspections are impacted by fatigue and distraction. In addition, different operators measure differently, even when the same gauges are used. Operator variation sources include part temperature, location, pressure, and orientation. Non-contact gauging has many positive features, including speed, accuracy, and digital connectivity. This is a fast-growing segment and includes machine vision, air gauges, and lasers, both fixed and scanning. However, most non-contact instruments still require staff to insert and remove parts, so the opportunities for automation are also strong for non-contact gauges. Manual gauge companies are working to catch up with industry needs. Most brands now offer electronic data collection, wired, wireless, typically where the inspector will push a button to send data, and every gauge is seamlessly connected to the Internet of Things. But the challenge remains that each part must be handled by an inspector. These are some of the challenges we hear from quality managers. Skilled inspection staff are retiring. Critical metrology know-how is being lost and needs to be retained. Labor costs, even at minimum wage, are too high for full-time, rote manual inspection. Shortages of qualified and interested replacements limits the ability to replace the people that have left. There's a need for more accurate real-time measurements to improve internal processes and to satisfy customer demands. And ultimately, the need to increase capacity faster than headcount. Hard tool automated inspection for mass production is long established. For example, in 1961, the first Unimate robot was installed at General Motors. This chart lists the unique features of Agile automation when compared to hard tool automation. First of all, there's the comparison. One comparison is that turnkey automation is generally proprietary versus Agile automation uses open source tools such as Cobots, end-of-arm tooling, and sensors. Hard tool automation is a best fit for mature and fixed processes with limited variations and greater than 100,000 parts per month, while Agile automation is ideal for new and dynamic processes with high mix and small batches, and generally for parts in the tens of thousands per month. Continuing with the comparison, hard tool automation generally requires a system integrator for both creation and support and deployment. You're generally talking about $1 million per workstation with an ROI of many years and the time to deployment, the project time is greater than 12 months. By comparison, Agile automation can be done independently using your in-house team. Typical workstation cost is $100,000 or 1/10 the cost of hard tool. ROI less than a year, and the project time, the time from purchase to deployment, is typically 3 months. So now I'm going to move to a specific example of Agile automation, and this is Cobot Caliper inspection. Some of the unique features of a robotic caliper inspection are it can fit in existing facilities and workflow. It operates safely next to staff. The features integrated are pick, measure, record, and place. That is picking parts from known locations, measuring the features using the caliper functions, recording the data and logging the data to a QMS system, and placing the parts in a known output location. A key advantage of this tool is the fast redeployment for high-mix manufacturing. Return on investment is an important metric for any capital investment. And in this case, I'm using an online calculator that's available at the website shown from RIA. And this starting point shows an initial cost of the Cobot workstation with installation and training of $100,000. And if you follow through the steps 1 through 6, you can see the parameters entered: 2 shifts per day, 5 days per week, 50 weeks per year, annual labor cost per operator, number of operators, percentage of labor required to operate the workstation, expected productivity gains. And following this website calculator, we come up with an ROI for a Cobot workstation that's less than 10 months. In the previous ROI analysis, I did not include other savings. Here are some examples of the additional benefits beyond ROI. You have a more engaged team. You reduce turnover and training costs. You improve gauge repeatability and reproducibility. That's gage Rnr. You reduce measurement variations, reduce scrap and rework. You improve process yields. You improve on-time deliveries. And finally, you increase customer satisfaction. So now we're going to talk about how to get started. This is a list of key ideas that are important to think about as you think about implementing collaborative automation. You want to think about incremental automation, a step-by-step approach, an approach that allows you to deploy workstations in months rather than years. You want to pick your most visible and worthy tasks that give you the greatest bang for the buck. You want to optimize the human and the robot work and find that optimum balance, with people being best at seeing, manipulating, overcoming the unexpected. And robots are best at repetitive, logical movements to known locations and making repeatable part measurements. This is aligned to the philosophy of our partner, Universal Robots. And here's a quote from Joe Campbell from Universal Robots about identifying the most worthy steps first, the worthy automation tasks first. A robotic caliper is a metrology instrument, and so it's critical to select the right fingertips for the measurement that's being made. And here's a chart that provides some examples that follow well-established metrology practices. Where do you use flats? Where do you use hemispheres? And where do you use spherical tips? And of course, there are many other possibilities. Gauge selection, the robotic gauge selection is the next critical step. And as we walk through this, we recommend that you first try automating your existing methods. What I mean by this is that if you're using a manual digital caliper today, that you should look for a robotic caliper to make the same measurement. And when you do this, this expedites the validation and correlation studies. If you completely change your methodology for part measurement, it's going to extend the project and perhaps the development time. You need to understand the part feature you're measuring and the tolerance T of that feature. And we're going to talk a little more in the next slide, but we need to understand that we have sufficient gauge Rnr with a goal of that being less than 10%. The example shown here is robotic calipers with 2.5 micron resolution on a UR robot. So let's apply the gauge Rnr calculation to a sample part. We've already talked about establishing the part tolerance T, and that is simply the tolerance on the drawing. It's a tolerance of the feature. In this case, M5 has a tolerance of plus or minus 150 microns. And we interpret this as a 3 sigma value. Next, we have to determine the repeatability of the measurement using our gripper caliper. And the repeatability is P, gauge precision, P, is a plus or minus 3 sigma value. So if you look at the ratio of P over T as a percentage, a capable gauge has a percentage less than 10%. So let's look at some actual data to flesh out this example for gauge Rnr. So we have 10 parts that have been measured 5 times, the M5 feature. And these 10 parts, you can see in the columns 1 through 10, have a calculated sigma that's shown in this row, and a sigma squared in this row. And the P is the plus or minus 3 sigma, which is just 6 times the sigma value shown here. So you can easily calculate here based on the T being plus or minus 150 microns, then these are the calculated gauge Rnr values for each part. And they range from 0% to 4.9%. You can also combine them together using well-established principles for combining sigmas and come up with a overall gauge Rnr of 3.6%. So the robotic caliper is clearly capable of measuring the M5 feature. So now let's apply the gauge Rnr more broadly to understand how a robotic caliper can be used in for various manufacturing processes. So we're using a p-value here, a precision value of plus or minus 5 microns as a conservative estimate of the precision of our gripper caliper. And we look at various processes from machine to 3D printing along the top. And we look at in the purple, we show the range of precision that may be required or may be necessary for these operations, with machining, of course, being the most demanding and could even be much less than 18 microns. Well, you can see there's many manufacturing processes where a robotic caliper has excellent gauge Rnr for inspecting parts. Each gripper caliper requires that a reference be set whenever fingertips or other parameters are changed. These reference standards are embedded in the automated workstation, and the references can be closing the fingertips to contact, that's simply 0, a gauge block of a certain dimension, a gauge ring of a certain diameter, or a golden part that's been certified as a suitable reference for a particular part measurement. You can set and check references as often as needed for any specific process because it's fully programmable in the robot program. To create an automated inspection process, you use the Cobot Teach pendant with its easy-to-use graphical user interface. It's a very intuitive scripting application. Process steps are created in sequence, including things like open and close grippers, measure part, J moves or L moves for the robot. Each part has its own unique program that can be stored in the Teach pendant and brought up whenever a specific part needs to be measured. Embedded in the inspection process steps, the robot script, are the commands to send ASCII data to the PC file or to a quality management system. And the data can be a part number, a serial number, the date, time, etc. This video shows the complete QSpan workstation deployment. A universal robot model UR3E has 3 gripper calipers installed. Reference standards are integrated for both inside and outside measurements, a ring gauge and a gauge block. Each gripper has fingertips that are matched to the features being measured. This workstation automatically measures 5 different features on the sample part. Each measurement is sent using ASCII characters to a separate computer, a CSV file, or a QMS database application. Engineered trays are used for fast parts in and parts out loading and unloading. The locations of parts in all trays are easily taught using the Cobot controller. A QSpan application is loaded in the UR-Teach pendant. This application enables seamless operation of the caliper grippers in the same program that commands the robot movements. Sample robot programs are included. This workstation is mobile, fits through a 30-inch doorway, and operates on 115-volt wall power. So let's wrap up with these takeaways. Cobot-based inspection tools provide fast deployment and short ROI for small batch, high-mix manufacturing. They reduce costs and increase competitiveness. The best practice for implementation uses step-by-step automation. You need to find the Goldilocks zone, the balance of people and robots working together, where people are flexible and innovative, and robots are infinitely patient, predictable, and precise. Robotic inspection tools can elevate your quality teams by automating tedious and error-prone measurements, improve your recruitment and engagement, reduce turnover, and reduce retraining costs. I thank you very much for your attention and hope to meet with you soon, either by phone or email, or perhaps even in person.